Welcome back to another day of linear algebra mastery. We have our 14 flashcards due today. I knew they were coming up, so let's go. What can you say about a number of solutions of a linear system? It's either 0 solutions, 1 solution, or infinitely many solutions. There's no other options. Cool. No other possibilities. Next, we'll see that in 17 days. What is an augmented matrix of a linear system? Basically, it's a matrix that represents the linear system. It's like the linear system's translated into a matrix. A rectangular array of numbers that represents the linear system. I'll call it hard because I didn't get the rectangular array part. But what is an homogeneous linear system in variables x1, x2, xn? A1, x1 plus a2, x2 plus plus an, xn equals 0. And when I say a2, I mean I'm saying a sub 2. What 3 basic algebraic operations can you perform on an equation of a linear system without altering its solution set? You can swap 2 equations, like positions. You can multiply both sides of an equation by a non-zero constant, I believe. And then you can add a multiple of one of the equations to another. Yep. Add a constant times one equation to another. Yeah, that's basically what I meant. That's what I meant. Maybe the language isn't exactly right. What is an ordered n tuple called in n equals 2? Ordered pair, n equals 3, ordered triple. Boy, it's an ordered triple. What does it mean to say that a linear system is inconsistent and has no solutions? How might you express a solution of a linear system as an ordered n tuple? You basically say parenthesis s sub 1, comma s2, comma comma sn parenthesis. What is a system of linear equations also called a linear system? What is it? Is a finite set of linear equations. What is meant by a solution of a linear system in the unknowns? x1, x2, xn. Basically, solutions are values that can be substituted for the x. So say x1 equals s1, in which it makes all the equations true, all the statements true. Yes, all equations true statements. Substitution makes each equation a true statement. Okay. I'd say hard. That was close, but not quite. What are the elementary row operations on a matrix? The same damn things we said for the algebraic manipulations. Switch 2 rows, interchange 2 rows, multiply through by a non-zero constant, multiply through one row by one non-zero constant, and add a constant times one row to another row. What is the effect on the solution set of a linear system if an elementary row operation is performed on its corresponding augmented matrix? There's no change to the solution set. What is another name for the variables in a linear system? Unknowns. What is a linear equation in the variables x1, x2, xn? We've already done this. Instead of 0, like it was an homogeneous one, or homogeneous, it's going to be b. What does it mean to say the linear system is consistent and has at least one solution? Cool. That's how you do it. And now we can recall about what we learned yesterday. What did we learn about yesterday? Right. Well, one thing I remember is we learned how to get an augmented matrix into reduced row echelon form. So that's cool. How do you do that? First thing you do is you get it into row echelon form. Well, cool. How do you do that? Okay, start with finding the leftmost column that has a non-zero digit, at least one non-zero digit, meaning it's not all zeros. Cool. Then you, if necessary, make sure that the top row has a digit in that column. So you maybe have to swap some. Swap a row to get a digit in that top of the column. Then you're going to multiply through that top row by basically a constant to get the leftmost digit to be 1 to get a leading 1. And then you basically, after that, you're going to get rid of everything below the leading 1 by adding a constant times the multiple of the first one, or constant times the first row, and adding that to the rows below it in order to eliminate everything below the leading 1. Okay. Then you basically, now you've done that row, you lock that into place and basically ignore it. Now you treat everything below it as its own new matrix and repeat those steps again until basically you have leading 1s and nothing below the leading 1s. Okay. That's row echelon form. And then to get reduced row echelon form, you're going to start from the bottom leading 1, and you're going to start doing the same thing where you're adding a constant times the bottom row to eliminate everything above the leading 1. So you're getting rid of all the digits in the column above all the leading 1s, one by one, starting with the lowest one. There you go. That's how you get reduced row echelon form. What else we have read about? General solution set. So, okay, parametric equations. So I think when you've got a set, or you've got parametric equations that basically represent the solutions, or are able to be solved for a solution, or a linear system that has infinitely many solutions. You call that a general solution, I believe. As far as the parameters go, for parametric equations, you can use any variables you want as long as they don't conflict with the linear system. But typically for typically for 3 unknowns or less, you're going to use T, or S and R, or S and R and T, or something along those lines. Those 3. Anytime you get more than 3 unknowns, you're going to start using probably T sub 1, T sub 2, ... T sub n for your parameters. So how about solving linear systems that have free variables? Basically, you're going to solve the leading variables in terms of the free variables, and then substitute the parameters in for the leading or for the free variable or free variables, and that's how you solve linear systems with free variables. I think we already discussed that yesterday, but I'll recall it again. It's we already did that yesterday. Never mind. I remember doing it. They're variables that are not associated with leading 1s in a reduced row echelon form augmented matrix. Okay. Cool. Got that. General solution. Parametric equation to solve for a linear system with infinitely many solutions. Cool. Got that. Yeah. Wow, we got everything. That's why I love math textbooks. I'll tell you that. There's no fluff. There's no stupid details that don't need to be there. It's all just straight up, here's what you need to know. No words that get in the way. All right. So now I'm going to continue reading, and I'll be back to recall in a little bit. All right, guys. So just learned about some terms. So the algorithm, which I described already today, that is known as the Gauss-Jordan elimination method. It has 2 phases, the forward phase and the backwards phase. The forward phase is when you're eliminating the constants below the leading 1s, and the backward phase is when you're eliminating the constants above the leading 1s. If you just have the forward phase, that's known as Gaussian elimination, which is the title of this chapter. So Now we know what Gaussian elimination is. We know what Gauss-Jordan elimination is. And we know what the forward and backward phase are. There was a little historical note on Gauss and Jordan. Wilhelm Jordan, and Carl Friedrich Gauss, two Germans. Gauss didn't come up with Gaussian elimination, but he popularized it when he predicted the orbit of a asteroid. And Wilhelm Jordan further popularized the elimination method in his book on geodesy, which is about measuring earthly objects. It was called Earth shapes. All right. Then we got an example of how to do, or just an example of Gauss-Jordan elimination, which I'm pretty confident we can do already. So now we're into a section called homogeneous linear systems. Homogeneous linear systems, again, we just got quizzed on that. They have 0 equals 0, no b value, or b value equals 0. So yeah, I've got only like less than 5 minutes, so I'll read a little bit and recall and call it a day. All right, wrapping up for today. So they're just talking about the nature of homogeneous linear systems, since the constant b is equal to 0 in homogeneous systems. Homogeneous linear systems. They're all consistent. Why? Because there's always at least a trivial, what is known as the trivial solution, in which all the unknowns are equal to 0. So 0 equals 0. So their homogeneous linear systems are always consistent. If the solution in which all the unknowns are 0, that is known as the trivial solution. Any other solutions other than that will be known as non-trivial solutions. So really, homogeneous linear systems only have two possibilities. You can have one trivial solution, or you can have infinitely many solutions, which consist of one trivial solution and infinitely many other non-trivial solutions. All right. So we're in this section on homogeneous linear systems. We get into an example of a homogeneous system. Then we get free variables in homogeneous linear systems, which we've already learned what free variables are, so that'll be interesting. See some summation notation. Gaussian elimination and back substitution. Some facts about echelon forms. Round off error and instability. All right, so we got plenty more to learn from this section, but I'm sure the meat of it we've already learned. Being the Gauss-Jordan method. We're at the bottom of page 17. So we've read up almost 7 pages in this chapter, and it is 12 pages long, so we're over halfway done. Yeah, it's great to keep learning and making progress every day. So I'll talk to you guys later. See ya.